Section 12.2, question 16. Set up iterated integrals for both orders of integration, then evaluate the double integral using the easier order and explain why it's easier. We're doing the double integral of x squared plus 2y dA over region D. Region D is bounded by y equals x cubed, and x is greater than or equal to 0. Let's see, y equals x is that perfect diagonal line. Supposed to go through the origin. Y equals x cubed is a twisty cubic, which starts at the origin, curves and goes up. This will intersect at 1, 1, which could be found easily by setting up x equal to x cubed and solving. Of course, it's going to intersect at the origin as well. And x is greater than or equal to 0 means that you are currently looking at the lamina that we are integrating over right here. Kind of that banana shape. Okay. Now, let's set up both orders and see what happens. Integral, parentheses, integral. We'll do dx first, followed by dy. We are integrating x squared plus 2y. And if we do the dx integral first, then we need to know what x equals on the left and what x equals on the right. Well, on the left, x is equal to y. And on the right, x is equal to y cubed. No. Y is equal to x cubed, which means x is equal to the cube root of y, or y to the 1/3. Which means for our inner integral, we would be going from y to y to the 1/3 power, or the cube root of y, if you will. And then the outer integral, we would need to know what y equals as constants on the bottom and top, which is 0 to 1. And then this will be versus the other order, x squared plus 2y dy, and then dx. All right, if we're going to do the dy integral first, we need to know what y equals on the bottom and what y equals on the top. The x's were left to right, the y's were bottom to top. On the bottom of the lamina, we have y equals x cubed. We were given that. And on the top of the lamina, we have y equals x. Then the x's, constants from left to right, are from 0 to 1. Am I missing something here? Because I don't think either one of these are that difficult. They're just powers. I mean, how bad can that be? Make sure I'm not missing something here. No, problem's written correctly. Because I am having a hard time to see which of these is easier. I guess maybe the bottom one would be easier because it doesn't involve cube roots, doesn't involve 1/3 powers. But at the calculus 3 level, saying that something is easier because its exponent is a whole number instead of a fraction, I don't think it's a huge justification, but if you had to ask me which is easier, that's what I would go with. So we are going to evaluate the bottom one. Only because, unless I'm missing something here, only because there's no cube roots, there's no 1/3 powers. All right, so if we're going to do that, then we need to get everything set up. We're going to do the integral from x cubed to x of the integrand dy. All right, so we're going integral x cubed to x. The integrand was x squared plus 2y. And we're going to do dy first. That's what it was, wasn't it? Yes, x squared plus 2y. All right. Integrate with respect to y. Well, x squared is a constant with respect to y, so its antiderivative is x squared y, plus the antiderivative, or an antiderivative of 2y is y squared. And this is going from y equals x cubed to y equals x. All right. Letting y equals x in the antiderivative gives us x squared times x was just x cubed, plus x squared when y equals x, minus what we get when we substitute y equals x cubed. So we get x squared times x cubed, which is x to the 5th, plus x cubed squared, which is x to the 6th. No like terms whatsoever. We'll just leave them in the order that we see them. Normally I would write them from highest to lowest power, but my two highest powers are both negative, and so I'll just leave them at the end. Leave the positive terms up front. All right, so this is the inner integral, and the outer integral, I believe, which is from 0 to 1. Yep. Going 0 to 1 of x cubed plus x squared minus x to the 5th minus x to the 6th dx. This is fairly trivial. Our antiderivative is 1/4 x to the 4th plus 1/3 x cubed minus 1/6 x to the 6th minus 1/7 x to the 7th. This is going from 0 to 1. Luckily, 0 will annihilate the antiderivative, so we really just have to focus on the 1, but the 1 is easy because 1 to any power is 1. So basically, we're just combining the coefficients. 1/4 plus 1/3 minus 1/6 minus 1/7. And again, the evaluation of the antiderivative is 0, so that's virtually ignorable. Now we just got to put all this together. Geez, what would a common denominator be? Well, 3, 4, and 7 have no common factors, so I'd have to multiply those. But the 3 times 4 would be a multiple of 6, so we just got to multiply 3, 4, and 7. 3 times 4 is 12. 12 times 7 is 84. And let's just talk this out. To get an 84 in the first fraction, I would need to multiply by 21. So the first numerator becomes 21 plus second fraction, the denominator is 3, and you need to multiply by 28. So we would get plus 28 minus the third fraction's denominator is 6, and I would have to multiply by 14, I believe. Yeah, so you get 14. And then the last denominator is 7, and I would have to multiply that by 12, so we get a 12. So we have 21 plus 28 minus 14 minus 12. Let's see. 21 minus 14 is 7. 28 minus 12 is 16. So 16 plus 7 is 23. So I believe we get 23/84. I'm going to do this the other way around just to make sure that answer is correct. In other words, I think I'm going to go ahead and do it with the dx first, even though our limits of integration involve fractions, from y to y to the 1/3. All right. So what would happen if we had done the other one first? Integral from y to the 1/3 power. That's a messy 1/3. Let's make that look better. 1/3 of x squared plus 2y. We'll be doing dx first. Let's grab all this, move it to the left a little bit. Okay. The antiderivative with respect to x is 1/3 x cubed plus 2yx or 2xy. And this is going from, let's make that a little bit better. And this is going from, we just did dx, so x equals y, 2x equals y to the 1/3. All right, let's see. If we put in y to the 1/3, we get 1/3 times x cubed, but x becomes y to the 1/3, and then 1/3 times 3. So we get 1/3 y plus 2yx. If we replace x with y to the 1/3, we get 2y times y to the 1/3. Add the exponents, we get 2y to the 4/3. Minus, and when we put in x equals y, we get 1/3 y cubed plus 2y squared when x becomes y. No like terms. So for the outer integral, which is also from 0 to 1, we would just integrate what we see, dy. 1/3 y plus 2y to the 4/3 minus 1/3 y cubed minus 2y squared dy. Let's see, the antiderivative would be 1/6 y squared plus All right, 4/3 becomes 7/3. So y to the 7/3. Reciprocal of that is 3/7 times 2 is 6/7 minus 1/12 y to the 4th minus 2/3 y cubed. And again, this is going from 0 to 1. 0 will turn the antiderivative into 0. So we can just focus on the 1, which will give us 1/6 plus 6/7 minus 1/12 minus 2/3. Let's see what that equals. Common denominator is still going to be 84. Yeah, 7 times 12 is 84, and 12 contains both 6 and 3 as factors. All right, so to turn 6 into 84, we would multiply it by 14, so we get 14. To turn 7 to 84, we'd multiply by 12. 6 times 12 is 72. Minus, to turn third fractions, denominator 12 and 84, we multiply by 7. And then minus 2/3. To turn 3 into 84, we would need to multiply by 28, I believe. Yes, 28 times 2 is 56. So now we would have to put together the numerators terms. Let's see, 14 and 72 is 86. 86 minus 7 is 79, and 79 minus 56 is 23. Is that not what we got before? Oh, good it was. That answer just sounded funny. And honestly, I don't think either of these approaches was more difficult than the others. I guess it's a matter of opinion, but I think the one they were going for was to do the bottom one first because the limits of integration involved integer powers of x as opposed to the other order up here, which involved non-integer powers of y. So whatever.